You know the periodic table of elements, right? It's got to be one of the most iconic charts in all of science. But have you ever stopped to think about why it's shaped the way it is? Well, the whole thing is dictated by the strange, fascinating rules of one tiny particle, the electron.
I mean, seriously, look at it. Why that shape? You've got these different blocks, these weird gaps, and then those two rows just kind of floating at the bottom. It looks a little random, doesn't it? But it turns out there is a deep, elegant logic hidden right there in plain sight.
And that logic, the secret that unlocks basically all of modern chemistry, it all comes down to the electron. If you can wrap your head around its bizarre, counterintuitive world, you can understand why matter itself is structured the way it is. So, to figure out how electrons build all the elements, we first need to know where they, live inside an atom. And the best way to think about this is that every single electron has its own unique four-part secret address. Now, in physics, we call this address a set of quantum numbers. It's basically a code that tells you everything you need to know about an electron's energy and where it's likely to be hanging out. This is the fundamental organizing system for the entire atomic world.
So this address has four parts to it: the principal, the orbital, the magnetic, and the spin quantum numbers. Let's break down what each part of this code is actually telling us.
First up, we've got N, the principal quantum number. Think of this as the state in our address. It tells us the electron's main energy level, or its shell. So an electron in the n=1 shell is super close to the nucleus with low energy, while one way out in the n=3 shell has much more energy.
Next is L, the orbital quantum number. If N is the state, L is like the city. It actually defines the shape of the orbital. That's the 3D space where you're most likely to find the electron. And as you can see, they come in these really distinct shapes, like a perfect sphere for an s orbital, or a kind of dumbbell shape for a p orbital.
Then we get even more specific with ML, the magnetic quantum number. This is the street name. It tells us how those orbital shapes are actually oriented in 3D space. So for that p orbital, is the dumbbell lined up with the x-axis, the y-axis, or the z-axis? This number sorts all that out.
And finally, we've got the house number MS, the spin quantum number. This one's a little weird. It's an intrinsic property of the electron itself, and it can only have one of two values, +1/2 or -1/2. We usually just call this spin up and spin down. There's no real-world equivalent for it. It's just a purely quantum thing.
Okay, so now we have the complete address system for any electron. But how do electrons decide which address to move into as they fill up an atom? Well, it turns out there are a few simple rules for how this atomic real estate gets occupied.
The first and most important rule is the Aufbau principle. And honestly, it just says that electrons are lazy. They will always take the spot with the lowest possible energy first, before they even think about filling up higher energy spots.
But the order they fill in isn't always what you might guess. So electrons fill the 1s orbital, then 2s, 2p, 3s, 3p. But then something weird happens. They jump up and fill the 4s orbital before they go back and fill the 3d orbital. Why? Well, because of some complex forces inside the atom, that 4s orbital is actually at a slightly lower, more stable energy level. This very specific filling order is literally the blueprint for the entire periodic table.
Then you've got two more rules that basically prevent total chaos. First, the Pauli exclusion principle says that no two electrons can have the exact same four-part address. So, if two electrons have to share an orbital, they must have opposite spins, one up, one down. And then there's Hund's rule, which says that electrons prefer to have their own space. When they're filling up a subshell, each orbital gets one electron before any of them gets a roommate.
So these rules explain how atoms are built, which is cool enough, but they also explain something we can actually see with our own eyes, light. The behavior of electrons and their little energy levels are directly tied to the light that atoms can give off or absorb. See, when an electron absorbs just the right amount of energy, it can leap up to a higher energy shell. But it can't stay there. It's unstable, so it falls back down. And when it falls, it releases that extra energy as a particle of light, a photon. The Rydberg equation here just shows how the exact wavelength, or the color, of that light depends on which two levels the electron jump between. And here's the really cool part. When electrons fall down to that n=2 level, in what's called the Balmer series, they emit light that we can actually see.
Okay, we have the electron's address, and we know the rules for filling up an atom's real estate. Now for the big payoff. Let's see how this all clicks together to explain the shape of the periodic table. This is the big aha moment.
The real genius of the periodic table is that it's a map of an element's properties. As you move across a row, we call that a period, or down a column, we call that a group, the properties of the elements change in very predictable ways. We call these periodic trends.
And the key, the absolute key to understanding pretty much all of these trends, is a concept called effective nuclear charge, or ENC. Here's how to think about it. An outer electron is pulled in by the positive nucleus, right? But it's also pushed away by all the other negative electrons between it and the nucleus. That's called shielding. The ENC is the net positive pull that the outer electron actually feels.
So let's see what happens when we move across a period, from left to right. Every time you take a step, you add a proton to the nucleus and an electron to that same outer shell. But because those new electrons are in the same shell, they don't really shield each other very well. So that pull from the nucleus gets stronger and stronger. The ENC increases, and it yanks that outer shell of electrons in tighter.
Now, what about going down a group? Well, every time you move down a row, you're adding a whole new shell of electrons. This new outer shell is way farther from the nucleus, and it's really well shielded by all those new layers of electrons underneath. So the outer electrons feel a similar pull as the element above them, but they are just much, much farther away.
So, let's put it all together. This constant tug-of-war directly changes an atom's size and how it behaves. As you can see here, moving across a period, that stronger ENC pulls the electrons in, so the atom's radius gets smaller. And since those electrons are held so tightly, it takes more energy to rip one off, so the ionization energy increases. But when you move down a group, adding those big new shells makes the atom bigger. The radius increases, and that faraway outer electron is way easier to pluck off, so the ionization energy decreases. It all makes sense.
And this isn't just some abstract theory. These quantum rules are the foundation for practical tools that scientists use in the lab every single day.
For example, take the Beer-Lambert law. It's a simple little equation labs use all the time to figure out the concentration of a colored solution. It works by shining a specific color of light through a sample and seeing how much of that light gets absorbed. And why does that work? It's because the number of dye molecules in the solution determines the number of electrons that are perfectly set up to absorb a photon of that exact energy and make that quantum leap. More molecules means more electrons making the jump, which means more light gets absorbed. It's literally quantum mechanics in a test tube.
So after all of this, we're left with a pretty wild thought. We've been talking about orbitals and shells this whole time. But remember, these are just maps of probability. They're clouds of chance. We never know exactly where any electron is. So if the entire solid world we see around us is built from atoms, which are themselves built from these fundamental clouds of chance, what does that really mean for the solid, predictable world we think we live in?